Okay. Okay, so thanks for the invitation. I'm from University of Nevada, Las Vegas. And my family name has same spelling as Wei Zhu's family name. And to confuse things a little bit more, we both work with Shu Bodong and wrote papers. And to confuse things even more, you will see Dongs in this talk. And that Dong is a different Dong, is Robin Dong in Victoria, who will visit here, will visit next semester. Okay.
So start the citations.
Yeah. So today I'll talk about using this substructure to review young planet populations. Okay. And a happy Halloween today.
Use the stick over there on the.
Oh, use stickers. Oh, it's okay.
That's not working.
Yeah. Okay.
Stick on the table.
Yeah. So because I use this to move the slides, so it's good. Yeah. So this work is collaborated mainly from my a brilliant graduate students, first-year graduate student Sanjia Zhang, and my postdoc Chaoqing Yang, and also collaborate with one of my longtime collaborators, Zhaohuan Bai, who is at Carnegie Institute of Washington and is a Hubble Fellow there. And also my groups include Zhaohuan, another postdoc, Hans Baylor, a postdoc, coming postdoc, and Ian is a graduate student. And part of this talk will be about this large AMA large program, D#. So this is a large program with a lot of people, with Sean Andrews as the PI. So I'll talk more about these later. Okay. So 2 decades after Phase 1 PXSB, we know planets are everywhere. We have 4,000 exoplanets. And they are exoplanets not only common, but they are also very diverse. Okay. These are the Kepler planets. These are planets in HR 8799 system. If we put them in the same scale, all the Kepler planets fit into a chronographs of HR 8799. Okay. So if we put the planets in the mass semi-major axis diagram, you could see them everywhere, from very close to the star to far away to the star, like 5 order magnitudes in radius, and also 5 order magnitudes in mass range. So it's really, really diverse. So the question for protoplanet disk study, the main thing is understand planet population, like planet formation, how we can form such diverse systems. So there are 2 ways. So the key question is how they evolve from this protoplanet disk stage to exoplanet stage. So there are 2 ways to think this problem. The first is we could study the young planet population, okay, or we could study the disk structures, like for example using AMA high-resolution observation to study disk structures and hopefully link these disk structures with young planet population. So we could ask where are young ones on this mass major axis diagram. So if we know young planet population on this plot, then we will be able to know where they form and at what time they form. And by comparing the young planet population with this mature planet population, then we know how they evolve with time. Okay. So this is the first kind of way to think this problem. The second way of thinking this problem is maybe we just do statistics for protoplanet disks. If we know statistics of protoplanet disks, then we can compare these disk statistics with the planet statistics and see if things could match together, if we could understand planet population by comparing the statistics. So these are the 2 ways to study planet formation in protoplanet disks. And this is what I focus today. So first I talk about these disk structures. So just recent several years, we have seen diverse disk structures at both near-infrared optical and radio, and or sub-millimeter to centimeter. We have seen a lot of axisymmetric rings and gaps. Okay. These are the ground-based observations, mostly from VLT. This is Hubble observation. So you see the rings. And this is from AMA observations. You see all these rings. Okay. And at the same time, we also see a lot of large-scale non-symmetric structures. Like near-infrared, we see like one side brighter than other part, and here's a. And sub-millimeter, we see some extreme cases. Like, for example, this case, there is non-detection on the other side of the disks, and this signal-noise ratio is more than 100. So all the emission come from one side of the disk, not the other part. So it's very, very extreme. And we've also seen things like spiral structures. This is near-infrared, have these beautiful spiral arm. And this is sub-millimeter, have these spirals. And we have seen things which have both spirals and these asymmetry clumps, like this one. Here is a spiral. So this source, this is a sub-limiter observation for this source. This is near field. So at two different bands, you see the same source looks totally different. Like here is two spiral, but sub-limiter is like two clumps at different position. Okay, so we have seen these non-asymmetric structures. And very, very recently, we have seen like disk shadows. Like here at the bottom, this is a near field observation for this source. Okay. Again, they look totally different. Okay, here and here. There's some limiter near field. But the cool thing about here is you see these two dark places here. So these dark places can be very well explained by a 70-degree misaligned inner disk. So if you have a very small disk, 70-degree misaligned, then at the node position, the inner disk will cast a shadow from the central star and produce these dark spots. And this is the Monte Carlo radial transfer calculation from this model. And they agree with the observation really, really well. You see, even the shape of these dark shadows match. So based on studying these structures, these images, we can even understand its 3D disk orientation, like the inner and outer disk misalignment. And such misalignment can also be seen at sub-limiter observation from velocity channel maps. You could see the velocity start to deviate from Keplerian rotation. That's due to the warping and the inflow to the inner part of the disk. So overall, we have seen these diverse disk structures. Okay, so the question is why they have such diverse structures, and if they are related to planets. Okay. So this is my first part of my talk. What's the observational signatures of planet? Yes.
Getting into the planet interactions.
Right.
Quick question: is there any trend of disk mass with the incidence of n=1 and n=2?
So there is not a clear trend in that. There is some trend on this pitch angle of this spiral with disk mass, actually. So we recently have a paper showing that when the disk is more massive, the spiral seems to wind up a little bit more. So there's some trend on the mass and the spiral pitch angle. Yeah, but the problem, the fraction of disks having these spirals actually seems more correlated with the stellar mass for Herbig A-star disks, which normally show these spirals. For Titori disks, most times were rings. So there is a bigger difference on the stellar type, central star stellar type. So maybe something process related with radiation could, yeah.
There's a correlation that all these are more massive.
Right. These are all massive disks. These are all massive disks. Yeah. Yeah, not typical. Yeah, not typical. This is observational bias here, right? So first I talk about the planet interaction theory. Then I'll talk about a new system, PDA-70. And this is a perfect test case for the planet interaction. Then I talk about the D-sharp and planet population. And finally, I talk about this, the statistics of protoplanet disks. And there is a problem people propose is this mass budget problem. And I say maybe we forgot some important physical processes like dust scattering, so which could naturally explain these problems. Okay. So first, the physics on planet interaction is actually very similar on the physics we have on Earth. It's basically waves and shocks. These are actually identical. So on Earth, we have waves. And when the wave becomes very strong, they become shocks. And the tools we study this phenomenon is doing numerical simulations. This video is from YouTube. This is a simulation to simulate what happens if you have an earthquake at the bottom of the ocean, how it will excite waves. And these waves become tsunamis when they go to these shallow water. And then they become shock break and damage to the seashore. Okay, so this is the tools people use to study waves and the shocks. And the tools we used is the same like code, basically the same kind of fluids, solving the same fluid equations. So in this case, we look at the disk face on, and the star is at center. And then we inject planet into the simulation. And then we are in the rotating frame of the planet. Okay, so Keplerian motion in this simulation become like this. This moves faster than the planet. This moves slower than the planet. Okay, so the waves we see in a water pond now becomes a spiral because there is a shear motion. So eventually here you see that planets interact with the disks. Planet launch waves. And when the waves become very strong, when the planet mass is large, waves become shock. When they become shocked, they open gaps. Yes.
The planet itself, is it a feature of having it in the planet's frame or an actual physical feature that's sort of like jittery?
Yeah. So this is some turbulence generated. This is more like, so you see it moves or shakes or a little bit. Yeah, so these shocks, here in this particular simulation, resolution is not high enough to resolve circumplanetary disks. But also these shocks a lot of time are not very stable. So you see they jiggle around. Yes, so here, in order to detect the planet, we could directly try to find the planet, or we could study the circumplanetary disk, for example. Or we could use indirect signatures like these gaps, or these spirals, or these blobs. Okay, these blobs that are due to instability at the gap edge. So these are all the observational signatures of planets in the disk when the planet interact with the disks. So first I'll talk about the spiral a little bit more. Okay, the spirals are basically density waves propagating in the disks. And these spirals, the inner spiral, because there's a high density here, they will attract the planet forwards. This is gravitational interaction between the spiral and the planet. So the planet will lose angular momentum and move outwards. Okay. The outer spiral here will attract the planet and drag the planet backwards. So the planet will, the planet will lose angular momentum and move inward. This is gain angular momentum, move outward. And due to the global geometry, these two forces are not balanced with each other. So this is the cause of the planet migration, one cause of the planet migration. So when these planets excite these waves, the waves, when they're very strong, for example, the planet mass is very large, then these waves will become shocks, exactly like tsunamis. When they become shock, then the wave could interact with the background disks and open gaps. Okay, so it's like this. So I talk about this gap opening. The gap opening process has been very well studied. So basically, the planetary torque to the disks is stronger than the viscous torque in the disk trying to close the gap. This work has been done more than decades ago. And this used 20 different numerical code. It's a code comparison project and carry out the same simulation. And you see most of these results agree with each other, not only the depth, but the width. Okay. So in this regard, there were some SPH simulations which somehow do not quite agree with, but most of the simulations actually agree with each other relatively well.
I think SPH results tell us more about SPH than about physics.
Okay, we don't get into an argument here. But overall, these gaseous primary gaps are very well studied. Okay, so we have pretty confidence that we have the physics we know the physics about this phenomenon. But there are some complications. The first complication is these ARM observations are more sensitive to dust particles than the gas. So dust and gas are not perfectly coupled in protoplanet disks. The physics is the same as you throw a basketball. If you throw a basketball, the basketball will feel aerodynamic drag, or you drive a car, you feel a drag force, it slows you down. So the same thing happened in protoplanetary disks. In protoplanetary disks, the pressure is high close to the star and low far away from the star. So there is a pressure gradient outwards. Okay, so if you have a gas in the disks, the gas is partly supported by this pressure gradient. Okay, so the gravity, balancing the gravity. So the gas particles will move at sub-Keplerian speed because the pressure force. But the dust particles, which is these basketballs, they are moving around the central star at Keplerian speed. So they move faster than the gas, then they feel the headwind from the gas, and they lose angular momentum and drift inwards. Okay. So to quantify their drift speed or the interaction with the gas, people normally use the Stokes number. Basically, the dimensionless stopping time. Just say how many orbits the particle will start to catch up with the gas. Okay. So the stopping time is related with particle size and the gas surface density. But the message here is that the dust particles in protoplanet disk will always drift towards where the gas pressure is maximum. So in a protoplanet disk, if the gas pressure is maximum close to a star, particle will drift towards the central star. Okay. And the drift speed is the highest when the Stokes number is close to 1. This is when particle has the fastest drift. So how this is related with planet disk interaction. So if you have a planet in the disks and open a gap, then you build a pressure maximum here and here. Okay. So now suppose you have gas and dust trying to move together to the central star. The particles will try to accumulate here where the gas is passing through. Okay. So this causes that dust and gas decoupled. And this is a numerical simulation, exact the same simulation as you've seen before, but now with different particles. This is small particle, and this is bigger particle, gets to planetesimal size. So you see when the particles, small particles, they couple with the gas very, very well, so that they almost follow the gas perfectly. But when the particle gets large, like millimeter, which is AMA probing, then the particles start to drift towards the gap edge or into these vortices. And the particle gets even larger, like centimeter, then they look like even narrower rings. Okay, they concentrate at the gap edge.
This is Jupiter mass?
This is this at this stage I think is around Jupiter mass. Yeah, around Jupiter mass.
What is happening to the kilometric size particles?
Yeah, kilometers. This is mean motion resonances, like 2 to 1. So these ones were very similar to the Saturn's rings mechanism in open gaps. So it's a little bit different. These were the mean motion resonances. So the pressure is not important anymore. It's basically unbody simulation become this. Yeah. So it's different.
So it's trace particles or is it a multi-fluid?
No, it's a particle. This is Lagrangian particles. We treated them as Lagrangian particles. And in this one, there is no back reaction. Yeah, in this one, there is no. We have recent work showing back reaction changes this picture quite dramatically if you have a lot of concentration. But this one does not have. Okay, it's just to show they look very different. Okay, the dusty gaps vary a lot depending on the different particle sizes. Okay. So this is the first complication. And the second complication is that planet interaction is actually a lot more intricate than we normally think. So you see this is a spiral launched by the planet. This is what our normal understanding of the planet interaction is. But if you look closely, you find that this spiral actually dies out. Okay? And there is a secondary spiral coming out at here. And recently we find this is due to the interference of various Fourier modes in the disks. They will not have the perfect phase. They have some phase shift. That phase shift will lead to this primary gap, primary arm disappear and secondary arm appear. Okay, so no. So this one, right? This gap, this is a spiral. This is kind of at the edge of the inner one. Okay.
So does the dark color mean
lower density? Lower density, right? So this lower density region separates this spiral and this outer spiral. So this is you have two waves. They are not perfectly have the same phase. When they propagate, they have some shifts.
a slight difference between the phase?
Yeah, so they have slight different phase between various modes. So this may not look like very important, but it turns out it can. I'll show later. It can be very important. One implication for that is, whenever you have a wave, when they steepen to shock, they will start to open gap. Okay, so normally people think planet interaction is these waves become shock and open gaps at these shocking distance. But if you have secondary waves, these waves, like here, this is a primary wave, they become shocks here, and then you generate secondary waves. These waves will become shock somewhere here. So in this case, this single planet will open 3 gaps. Okay? So this is a planet at r equals 1. These are the normal gaps opened by the planet. Okay? This is a horseshoe region, think about it. But this is a secondary gap opened by this planet. It's very far away from the planet. It's half of the distance to the planet. So when the planet mass increased, this wave shift even gets a little bit more. You have these tertiary spiral arms appear. And these tertiary arms will become shock here. In this case, a single planet opened 4 gaps in this simulation. Okay. So although these gaps are not very deep, and you require very high numerical resolution to resolve them because these are very inviscid. You are studying these wave properties. No, this is 2D, but we have done 3D. They look almost identical for these ones because the waves are these verticals, the free mode dominates. So they almost look like identical to 2D. But the point here is a single planet here opened 4 gaps. Okay. So a planet can open multiple gaps. If we see some gaps in disks, they may not harbor planets. And also we can use these gap positions to estimate the planet mass because now you can see from here whether the gap appear and the distance of the gap to the star or to the planet depends on the planet mass. So we can use this to estimate the planet mass.
How does the structure of the gaps change? So suppose that you change the mass of the planet continuously, right?
Right.
similar masses. So how do you go from 3 to 4 gaps? Like you have 2 gaps, one gap just splits into 2 gaps and started very close to one another and just drop off?
When the planet mass increases, if you do continuously, like this, then you will see these ones get stronger and stronger, more close to the central to the central planet. And this one, you actually see the tertiary gap here. But this tertiary gap had not become shock in this simulation. But then later they will become shock when the planet mass increases. Then you will start open gap here.
So all the waves are in all simulations, just that for small enough planets, they don't become shocks within the computational domain.
Exactly. So, and they propagate along long distance, right?
What's the difference between the left and right?
This is different. Sorry, this is different planet mass. This is a lower planet mass. I didn't label the planet mass. I should. This is the lower planet mass. This will be higher. This is like factor of 3 higher than this one. So when the planet mass increases, then you have these more waves generating the disk, which can open more gaps. Right.
This is, I mean, the location of the second gap seems to change.
Right. That's because these shocks shock earlier, a little bit earlier.
So it's not any kind of resonance location.
No. It's not written to the location. It depends on the shocking place. The shock earlier. Right. But this is more sensitive to the temperature, actually. Here we fix the temperature. But if we change the temperature, because the sound wave propagation depends on temperature, if you change this temperature more, this wave propagation will change a little more.
Because you rely on shock, how does it depends on viscosity?
So this is very low viscosity. This is like 10 to negative 4 something. Yeah. Right. If you add 10 to negative 3 alpha, you still have these, but much shallower. Yeah, this is 10 to negative 4. Alpha is 10 to negative 4, right? Yeah, these things get more complicated when we consider thermodynamics. And recently we are working on work where we add cooling in these ones, and then the shock can dissipate through the cooling process. This is isothermal simulation. So it will change these features too.
Why will it change, right? Because the value of the viscosity only changes the shape of the shock, but the width, it doesn't change the before and after the shock.
You mean the cooling? Or?
No, the viscosity.
Oh, viscosity. Yeah, the viscosity will make them shallower. Damp the waves. Right, damp the waves. Right. Okay, so these are the 2 complications recently. Then I'll talk about this PDS-70 system. And this is 2D, but we have done 3D. We haven't published the 3D. Zhaohuan has done 3D, but so far we look very similar. Yeah, look very similar. Oh. So PDS-70 system is this system is a weak line T-Tauri star. Is a K7 star. Is 5 million years old, and it has a 50 AU cavity. 50 AU cavity. And just last year, a planet was discovered within this cavity, around 22 AU from the central star. It's a 10 Jupiter mass planet. This is by VOT. And the difference between this candidate and previous candidate, we have so far have several candidates on young planet in disks. The difference between this one and the previous one is this one is very robust. This one has been detected at any instrument on VOT. Like at all the bands, from near-infrared to mid-infrared, and even with the integral field spectroscopy, spectrograph, like here. So we even have part of the spectrum. So now we are pretty confident this is a young planet in the disk. The mass, we are not sure, maybe 5, maybe 15, but there is indeed a point source inside this cavity. So with this planet detected, now we know where the planet is. We should be able to test all the theories we said before, like whether how the gap opening stuff and planet particles. So the first thing we could ask, the first order question is, how can a 22 AU planet open a 42, 70 AU gap, right? Yeah, kind of know, here is a K7 star. So the mass is around 0.7. The cap, yes, you have kinematic mass from the rotation, the AMA observations on that one too. So you know the incarnation also. I'll show some AMA observation later. So a single planet can do this work. Okay, so this is work with an 8 Jupiter mass planet, but on an eccentric orbit. But if you use a single planet, it requires some eccentricity of the planet. It needs to be larger than 0.2. And then And then the planet also needs to accrete so that it can deplete enough material around it, okay, to open this wide cavity. And very recently, there is another source discovered, also from VOT. This is from H alpha observation. They found the PDN70C here at 35 AU from the central star. And this source and this previous source is in 2-to-1 motion resonance. And this multiple planets scenario has been proposed many years ago to explain some of very wide cavities in protoplanetary disks. And recently, Zhaohuan have done this nice simulation showing that if you use this parameter for PDA70 with two planets in the disks, they will naturally migrate into 2-to-1 motion resonance and open a cavity around 50 AU. Okay, so now with multiple planets, we can explain this one. So if this observation is correct, it suggests that multiple planets are normally in mean-motion resonances if you have gap, or they should move into mean-motion resonance, and they can open a very wide common cavity. Okay. So right now, you can only just you are not really know whether they are trapped in resonance angle. Here it's just based on their distance and assuming it's a capillary motion.
That's not known that well either.
Yeah. It's not really have observation proof that they are really in mean-motion resonance.
You can't get radial velocities because the stars.
No. Yeah. No, it's too far away, right? The 35 AU, you cannot detect radial velocity. Yeah. This is just based on the distance argument. This simulation alpha is 10 to negative 3. So, yeah. You could decrease the alpha to make the gap a little bit wider.
You said it's a T-Tauri, so it's weak line T-Tauri.
Yeah, this is a weak line T-Tauri star. The accretion rate is around 10 to negative 10 solar mass per year. Yeah. So it's a very low accretion rate. Yeah, inside. Yeah.
Inclination of the sky fairly well constrained.
Yes, that's from ARMA observation. It's very well constrained. Yeah, I'll show ARMA observation here. Yes. So this system have also been observed at different wavelength. Okay, so this is a discovery paper. It's a Subaru sees observation at H band. Okay. This is ARMA recent observation. So just by eye, you can see at near infrared, the gap is smaller than sub-millimeter. Sub-millimeter is much bigger than near infrared. And also based on these rings, you could figure out the inclination. And based on the velocity channel maps, you can get the central star mass. Okay. So,
The one down in the corner.
right, this is the beam.
Barely resolved.
Oh yeah, the ring is barely resolved here, right. So this is from the gas dust particles simulation with two planets, and the gas can be compared with H-band observation. The particles compared with these. And also, just by eye, you can see the particles move much further away than the gas. This is because the particle trapping at the gap H millimeter. Okay. So again, the picture seems to still to holds that dust trapping could work. Particle indeed, at some millimeter, they are much larger cavity than near infrared. So far, theory seems to holds. And an interesting thing about PDN70 is there is a hint of the circumplanetary disk around it. This is from this H alpha lines. This is H alpha detection for PDN70 B and C. And H alpha lines normally are produced by hot gas. And in T-Tauri stars, H alpha lines are from the magnetospherical accretion. Okay. So if you just naively use the H alpha m dot relationship from T-Tauri star to planets, okay, which is tricky, then you will derive accretion rate of the planets around 10 to negative 8 Jupiter mass per year. Okay. So this is a reasonable number. With 1 million years, you will grow like 1% of Jupiter mass. It's not a hugely accreting disks. And another hint, there is something around the planet is
200 kilometers per second.
right.
That's a high number, isn't it? What's the escape velocity?
So if it's a 10 Jupiter mass planet, I think escape velocity is around, because Jupiter is much smaller. It's 1/10 of the solar radii. So, but the mass is 1,000 times smaller. I think it's around several hundred kilometers per second. It's 10 Jupiter mass, 10 Jupiter, right. Jupiter size, like several hundred, 200. Yeah, right.
The size from the
No, you don't know the size, actually.
The size from all the you said from the LDLT observations.
The planet size. The model comes, this model.
Yeah, exactly.
Yeah, constraint is around 1.5 Jupiter radii if they use that to fit. Yeah, so you have similar several hundred, maybe 1 to 200 kilometers per second escape velocity. So another hint that there is something going wrong is that when they do integral field spectrograph to mid-infrared, near-infrared, they see this axis. Okay, the blue curve here is the best fit planet-only model. But now they see some axis, and here the error bar is large, but here the axis. So this is very tentative. But if you assume that axis comes from accreting circumplanetary disks I did before, then the accretion rate of these circumplanetary disks is around 10 to 8 Joule mass per year. So roughly, so far it's okay. And another interesting thing is these two sources has been recovered from some limiter observation. So this is AMA observation. And there is some hint, the B and C were here. Not very clear. Yeah, it's like 5 sigma. But with AMA observation, sometimes 5 sigma is not really enough. This is rendered from the numerical simulation. So we could play with the dot size distribution, could kind of recover these. But if we use very high resolution, which the observation have been carried out, hopefully we'll see the results soon. That with this high resolution, we should see these point source detached from the ring and confirm whether these were real point masses. Yes.
So I just have a question between the panel on the left and the middle one, where you're looking at, I guess the disk that you're seeing there is larger than the beam size.
Right, right. So it's a more resolved, right? You are saying this is more resolved.
Physically, that it has that wider, the disk is wider, say, than that synthetic image. I'm just looking at.
Yeah, synthetic image seems to concentrate too much. Yeah, so maybe there's more turbulence, or maybe we use different dust sizes distribution. Here we play with the dust size distribution so that they could match these point sources. So it's not really a first principle simulation where we evolve everything. We kind of tweak the dust size distribution a little bit. But overall, it seems something is really going on around the planet. Whether it's a circumplanetary disk or some material, we are not sure, but it's consistent with CPD. Okay. So, so this is a rendering for this PDN-70 system. So we have done this one with the new Athena++ simulation. It's rendered by the California Academy of Sciences. It's the same people who rendered the first movie. Okay? But the first movie is made for them for their current planetarian show on New Horizon mission. Okay? And this movie is rendered for their next show on AMA. Okay? So because I worked with them before, so it's easier to work with me again. I just do this simulation for PDN-70 systems. And you can see the dust, which is the yellowish color trapped at the edge. And then you have two planets, one planet here and one planet here, and they are accreting.
It's not a bright spot.
Yeah, so the bright spot here is actually the horseshoe material. So there are particles trapped in the horseshoe. These spots can go away if you run the simulation for a really, really long time. But for this 3D simulation, we cannot run a really long time. So they have hot spots.
Optimistic about being able to see the background stars.
It's a, yeah. Oh, yeah. They actually do real ray tracing. These guys do real ray tracing, better than radio transfer we did. Because, and you see the dust is settled to the mid-plane.
The stars are not bright.
And you can even see shadows. You see these shadows. These were shadows cast by these ones. Yeah, I never thought about it. But when they do this ray tracing calculation, they actually see the shadows cast.
Oh, that depends on how.
Yeah, in reality, it depends on the vertical extent. Yeah. In reality, it's more complicated. Here, they just use my data, assume some opacity in their model, and then they do this rendering. It's more like just for rendering. For their shows, planetarian show is not that 100% scientific accurate. Yeah, it's a demonstration. Yeah. Maybe. Okay. Yeah, so now we have this single system. We're still trying to understand what's going on and what constraint can be put on planet interaction. But big question is, what about this young planet population? Okay, can we get anything out from these structures? And this is what I'll talk about this large program, D#. So this ARMA large program is 75 hours with ARMA, very long time. PI is Sean Andrews, a lot of people involved. And we have 4 graduate students, so they have a lot of work to do. And it's the highest resolution ARMA available at 1.25 millimeter. It's 5 AU resolution, also highest. And when we design this, the goal is to resolve the pressure scale height in the disk, because that's an interesting scale in propellant disks. And we want to get a 10% contrast. This is to get like a Neptune mass planet. If there are planets in the disk, we do some estimate. This is 10%. So it turns out we can do only very bright objects to get this 10% contrast. So we have 20 propellant disks. These are all full disks. So unlike PDA-70 system, you have a cavity. These ones do not have known cavity. So there's no known cavity, no envelope. They are all class 2 objects. So 10 objects in Ophiuchus and 10 objects in Lupus. Okay, so these are all the 20 disks you probably have seen. There are 2 binary systems, this one and this one. The binary in this one is somewhere here. I didn't show. But both of these binary systems have some spiral. It's kind of barely can see. With some imagination, you could kind of see there are some weak spiral. And there are also 3 systems with spirals. This one, this one, this one. Okay.
It's all dust emission.
These are all dust emission, 1 millimeter, dust thermal emission. And these are, most of them are T-Tauri stars. Okay. So besides all of these, most of the disks show gaps and rings. This is a common feature in this survey. So a lot of interesting stuff coming out, and we have 10 D# paper, and I will only talk about the last one. We try to use planet dish action to explain these gaps and rings and trying to get a young planet population. So it seems impractical to fit all the gaps one by one. Okay. It's, numerically, it's hard. So we decided to do a full parameter study for simulations. So the code we use is, again, this Dusty Fargo code. Is a 2D simulation. Gas is grid-based. The dust is Lagrangian particles. So we have 5 planet mass, from 10 Earth mass to 3 Jupiter mass, and 3 different disk turbulence level, small alpha, big alpha. So when the disk is more turbulent, the gap is narrower and shallower. And we'll also try very different disk thickness, different sound speed in the disks. When the sound speed is large, it's harder to open a gap. But when you open a gap, they will be wider. Okay, so we did this full parameter space study.
It looks like the gap has more of a asymmetry for higher alpha.
Right, exactly. Yeah, because you will, with the higher alpha, you will prohibit these instabilities at the gap edge, which are due to the shear. These Papalouzeau-Pringle instability. So these ones are already become non-axis symmetric, have vortex forming. But with higher alpha, they prohibit that happening. So they are more smooth, more like ring structure.
Well, but at the lower masses, on the other hand, it looks like it's more symmetric.
Oh, right, because you do. Oh, here you don't even open gap.
I understand, but say
Which one?
33 Earth masses.
This one. Yes.
One
Yeah.
on the right has a clear spiral density wave.
Right. Exactly. Here.
The one on the
Right.
left
It's more like a gap.
is more
Yeah.
axis symmetric.
Yeah. More axis symmetric
So-
ring.
So
Right.
the patterns are very much mass and alpha dependent.
Right. Exactly. So these are the 2 parameters: mass, alpha, and also H/R, thickness, this thickness dependence. Yeah. So in these simulations, we not only have gas, we have particles. So there were small particle and big particle. And in order to generate these ARMA observations, we need to give opacities to these particles. So small particle and big particle have different opacity. So we need to add them together. Okay. So I just run the simulation. So you see the small particles do not open a sharp gap, but the big particle open sharp gap. And then eventually we generate these synthetic.
You say small and big, that must apply to Stokes number.
Yeah, this Stokes number. So this is around 10 to negative 2. This is 10 to negative 1. But in the simulation, it's continually distributed with some size distribution. Here, we just pick 2 Stokes number, right? So some highlight. This is a highlight I really like. This AS209 system. This system have like 5 gaps and 5 rings. Okay, gaps and all the rings in one system. And when we fit this system, first we put a 0.3 center mass planet at 100 AU, trying to get these 2 major gaps. Okay? It fits. But the simulation also automatically gives this secondary gap. This is due to the shock of the secondary arm at almost the right position at here. Okay. And even shocking to us, the simulation gives us this gap. It's the tertiary gap, which kind of match this one. Okay, the blue one is observation. The orange one is the simulation. Okay, and then it even give you the 4th gap or the 5th gaps here. Okay, and eventually simulation run out of the inner boundary, and we cannot see whether this is related with that single planet. But overall, we could have a single planet in this system somewhere here, explain these 2 gaps, this gap, and this gap, and this gap, and this gap. Okay, so this is quite shocking to us. A single planet at 100 AU, it's able to generate 5 rings and 5 gaps automatically. Of course, here we kind of tweak the parameters slightly. There are still 3 parameters we can play with to get this good match. But this good match already suggests that, give us some confidence that these rings may be related to the planets in disks.
What were the parameters? What were the alpha and atroph R?
So it's the alpha atroph R, these 2 parameters.
10 minus 5, that's what you said earlier.
This one is 10 to negative 3. This is 10.
If you go back to your,
Oh, this one. Oh, yeah, these are 2 different models. This is 10 to negative 5, right? The second one we find is better if we use some alpha changes with radii. It gives you a little bit better fit. But this one already fits, could fit these ones. Okay. But this one, if we allow alpha to change, it will do a slightly better fit. So alpha varied, like here. Atroph R, this one is around I think 0.55. It's a little bit thin. It's a bit thin, you know. No, it's not constant. It's decreases. Atroph R decreases like negative 0.25. Yeah, 0.25, 1/4.
So H-bar decreases.
Oh, so CS, H/R CS over V5, right? So it's
It should increase.
yeah, increase is 0.25. Yeah, increase 0.25.
what's the normalization? He says a little bit low.
Yeah, 0.05 is a bit low.
At 100.
100 AU. You think at 100 is around 0.7. So there are some.
You want a really low sound speed, basically.
Yeah, you need a. Because otherwise, if you have higher sound speed, this gap will be a little bit further in, because these waves will be a little bit further in. So it will not give you this fit. Yeah, non-resistant to shock. Yeah. So yeah, something.
Look at the gas profile. What's that look like?
Oh, this is gas profile, the background, the gray. This is very, very shallow, right? These ones you cannot say they are gaps, but because they will trap particles, they will more look like gaps.
So,
Yeah.
and the other question is, can you see that in CO emission or something?
CO, no. With CO, you will be able to get these gaps if the CO is around center mass planets. So with center mass planet, this gap will be a little bit deeper, and then you will CO, you should be able to see. But right now, the CO observation is not that, cannot really tell you the gas surface density profile. Or if you use 18 CO, you should be able to see optical thing. But then the signal noise is not good for 18 CO. No, C18O.
Viscosity. So you said you ended up doing something that varies more. So I guess if your alpha viscosity is really just a way to parameterize.
Right.
Is there good physical reasoning for why you have that variation?
So there is some physical argument alpha should be higher, is that the surface density is lower, so X-ray and cosmic could penetrate through, so you will have more turbulence. But that's just the theory argument. It's not, no.
-3 and a Stokes max of 10⁻². These particles will be distributed vertically in the disk, right?
Right.
They won't settle.
No, for millimeter particles, you still have significant settling though. for millimeter Stokes number 10 to negative 2, you still have significant settling. Yes, yeah. Because the relationship between the scale height is h over, if you have alpha, right? It's, I think, square root of alpha.
I thought you were comparing. Anyway, you can go.
Oh, okay, yeah.
For this case, for the opening the main gap, you need alpha 10 minus 3, is that right? Sorry, 10 minus 5, 10 minus 3.
Opening this, in this model, alpha varying.
What is it, alpha?
No, one of the reasons why alpha is varied here is that these gaps, if this alpha is very small, they will develop some asymmetry in these 2D images. So that's why we increase the alpha. Alpha here in these, No, alpha increases towards outside. Outward, yeah, because if inside alpha is large, these waves won't be able to propagate to here. So you need very low alpha here. You allow these waves to propagate to the inner part. Yeah, surface density decreases, alpha increases. Yeah, that actually makes sense.
The outside means such a low mass planet. This is natural mass. How can a natural mass planet open such a wide gap if alpha
It interacts on particles.
No.
Oh, yeah, there's still gas. You can still open it because the disk thickness is not very high. H over R is 0.05. So when you get to the,
That's why they wanted to.
for example, 0.05, right? 10 to negative 3, 30 Earth mass could open something like that. So
And what's a star? Stars are 180
no, a star is around solar mass star. That's
Still,
more.
the gas.
Right, 0.05. Yeah, the gas is a bit thin. Yeah, but the near field observation suggests that this disk is very thin. This object is very faint at near field observation, suggesting that the disk is very thin.
Question, right? Because a lot of the heating out here is coming from the radiation.
Right.
The particles are set in the bed.
Yeah, you have less
Then
flaring.
The heating will be more vertically concentrated.
Right.
So it's a complicated system.
Yeah,
We're talking about gas temperature. As
No,
long as any kind of
No.
gas particle sees the star, the gas pair is going to jump to the H bar and come
No, but here is the temperature at midplane. So at midplane, dust and gas coupled. So it's most of the heating is by the dust absorption stellar light, right?
But it's very hard to make the gas there cooler by factor of 4. Okay, we can talk about
Yeah, okay.
It seems very hard to make.
Yeah, but this is another system. So I'll speed up a little bit. So eventually we have this planet mass estimate, but unfortunately the planet mass depends on h over alpha, h over r, and size. So there's a huge uncertainty. Okay. So, but we could put all these major gaps on this plot on the planet mass major axis. The 1 order magnitude uncertainty due to the alpha, 3 order magnitude uncertainty in alpha, h over r uncertain by a factor of 2, and particle size is uncertain by 2 order magnitude. But I have this population. But we only have one source, which is massive enough to say this is a Jupiter mass. So one source out of the 20 sources we have. So the current rate for 5 Jupiter mass planet and above is only 6%. Oh, it's not very high, not as high as we thought before. This is kind of roughly consistent with direct imaging results. But there is a huge population of this Neptune to Jupiter mass planets beyond 5 to 10 AU. The current rate is around 50%, a pretty high population for this one. In some sense, it makes sense because our solar system have Uranus, Neptune in this range. Okay, but we still need to confirm this large population, Neptune to Jupiter mass. So there's maybe microlensing future will be a good way to probe this population. Okay, so if we believe these gaps and rings are caused by planets, then the planet formation can be very efficient even further out at 10 to 100 AU. Still needs to be tested.
For the direct imaging, it's just that the sort of Neptune-sized planets are far too small to.
No, yeah, is that too faint? They are too faint to be observed, right? Okay, so then we have 5 minutes to talk about these statistics on planets. So a good way to study protoplanet disks is just do ARMA blind survey for all the disks in a star-forming region. Some were big, some were small, and compare with the planet statistics. So the first thing you want to ask is, what about the disk mass? Right? So the disk mass, people normally estimate in this way, assuming a black body radiation, optical depth effect. When it's optical thin, okay, tau goes to here, then its mass can be related to opacity. Assume some opacity, you get mass. This is what people normally done. And
Why would you get black body?
so this is black body radiation. When it's optical thin, 1 minus E minus tau becomes tau. And then this is dust thermal emission. So the source function is a Planck function.
So you get some thermal emission.
Yeah, it's a thermal radiation. Yeah, it's a thermal emission. Dust thermal emission, right? So if you get the disk mass, the dust mass is like this. This is the dust mass with the probability of a disk with mass larger than this one. But overall, the average dust mass from these blind AMA surveys suggests the dust mass is around 15 Earth mass. Very small amount of dust mass in protoplanet disks. So there seems to be a mass budget problem. The problem is illustrated here. So this solid curve is the dust mass with the central star mass. And when the central star, when the mass goes up, the disk is more massive. Okay, so basically you have more massive disks around more massive stars. And at the solar mass, this is around 15 Earth mass. Okay, oh here, 15 Earth mass. Okay, and these dots are the Kepler planet mass, estimated solid mass using some mass radius relationship. Of course, that's uncertain, so there are two curves. But overall, it suggests that for disk around solar mass star, you have enough material to explain Kepler planets. Barely enough, just factor of 2. But for low mass stars, you don't have enough disk material from AMA disks to explain the Kepler planets. That's just within 1 AU. Not to mention 10% FGK star even have Jupiters or super Jupiters. Okay, so apparently there is a mass budget problem comparing AMA statistics with Kepler statistics. So there are two solutions. The first is dust growth really early. Like people suggest we already have planet formed, like in atrial tau. So we don't have a lot of dust left. Another solution is that protoplanet disks are very optical thick. Okay, so there are more dust than observed. But this is not preferred from this D-sharp survey. So this is optical depth for these 20 sources. This is with radius. And you can see this dotted curve is where optical depth is equal to 1. Okay. So, yeah, from this formula. Go from here, you estimate the disk temperature, okay, which is kind of uncertain. Use Goldreich-Tremaine formula to estimate the temperature. And then you use this intensity measured and get optical depth. Okay. But yeah, it's not very accurate. And I'll argue that there are more issues here. So only 4 disks are optical thick. And even these 4, the optical depth is smaller than 3. Yeah, smaller than 3. And there is a mystery that a lot of disks plateaued around 0.6. Like here, never go above 0.6. And here is 209. Okay, never go above 0.6. Okay, something fishy going on. What's magic about 0.6?
It's not magical about 1 anyway, right? Because that formula about 1 is no sensitivity.
Yeah, you lose sensitivity. Yeah, when the tau is large, you lose sensitivity. Right.
0.6 is 1, isn't it?
Right. But I'll make an argument. 0.6 is important. So basically, from this argument, people don't prefer this optical thick scenario. Think, okay, these are optical thick. But I'll point out here that this formula only stands if there is no scattering. Okay. So imagine this is a disk. This is extremely optical thick. I is close to B. Intensity black body. This is mid-plane atmosphere. If there is no scattering, the photon will travel mean free path, absorbed and emit again. Okay. So the mean free path is 1 over absorption coefficient. Then only photons close to the surface can escape. Then the intensity will be emissivity times L, which sigma cancels out is B. Okay. So this is normally in the extreme optical thick regime. But now if we consider scattering, albedo is 3/4. So the scattering coefficient is 3 times the absorption coefficient. Then the photon will travel 1/4 of the distance before being scattered. Okay. And it will scatter 3 times before being absorbed again. So the total length here is still L, but it will scatter. So it will travel these steps, 4 steps before being absorbed. But because scattering process is more like a random walk, so the real distance between these two is smaller. Okay? So the effective mean free path is only half. And then only photons at the surface can escape. Okay? So in this case, intensity is reduced. So now if you consider scattering, the disk will looks fainter. So this is this is a simple argument, but if you derive formula, it's something like that. Okay. So beyond the normal term people used, you have this additional term which has albedo inside it. So if you ignore this term, you say tau is 0.6, or you could say tau is infinity, but I have some albedo. So they are equally to give you the same intensity. So this effect has mentioned, but somehow they were forgotten in this mass estimate. So scattering will make opto-thick disk look fainter. And because they make opto-thick disk look fainter, they make them look like opto-thin. Okay? So we could underestimate opto depth significantly. So because the time is pushing, I just show here, this is without scattering, you will think that, well, without scattering, this is like opto depth, the real opto depth, and these are mirrored opto depth. Okay? So it's less than 1. If you compare with D-sharp observation, okay, this looks very similar to this. They all plateaued around like 0.6, okay. And this, because we underestimate optical depths, we underestimate the disk mass. So this is the disk mass, the true disk mass. This is disk mass if we do not consider scattering. They are differed by the true mass by 1 to 2 order magnitudes. Okay. So at 1 millimeter, we could easily underestimate the dust mass of factor of 10. That's what I'm arguing. And considering that a lot of these real protoplanar disks, most protoplanar are really compact disks. For these compact disks, they are small, so we could underestimate the mass dramatically. Okay. So protoplanar disks can be more massive than we think, and we really need to go to long wavelengths like VOA. And we have one example now, H.O. tau. We have VOA observation at 2 different bands. And without considering scattering, mass is 0.3. With scattering, is 0.5. In this case, that the disk is already opto-thick, very opto-thick, at AMA band. And we have VOA observation before. So this mass estimate, even before scattering, is not, considering scattering, is not very bad. But overall, if you increase, considering scattering, you could increase the disk mass significantly. So including scattering can change our estimate of disk temperature and mass. And unfortunately, such correction is hard to make without long wavelength observation like VOA. So there are other applications. There's this luminosity size distribution relationship in protoplanar disks, and this can be explained by scattering too. And scattering have been memorized by polarization observations with AMA. So scattering is important. Have some implications for other things. So to conclude, we have seen dust gas and CBDs in these beautiful systems. And we have D-sharp with a lot of rings and gaps. And hopefully, when we build this young plant population, and I'm arguing that we may underestimate the disk mass significantly. So there is some link from here to here, and we still don't know the physical processes happening from early stage to late stages. Okay, thank you.
Are there any more questions?
We can talk about it.
So I have a question. So Hank Spruit has a paper from I think '87 when he developed similar solutions for spiral shocks. So
right.
You can compare it to your simulations?
Yeah, that's a self-similar solution for the spiral shocks. Right. So those shocks are really more stronger, much stronger shocks. Here, these are very weak shocks. Their pitch angle is more similar to these linear dispersion relation for waves in the disks. They start to deviate from the wave pitch angle slightly, not significantly deviate from the linear wave because these waves are very, very weak.
If I remember right, it's related to the aspect ratio, right?
Yeah, it's by H of R. Yeah, that's natural for both linear theory and nonlinear theory. Right.
Okay.
So I have a
Yeah.
question about these disks again. Can detect any of those in the gas?
The gas. Yeah, these have also, among all of these, around 10 of them have been detecting gas. Okay.
Gas to dust ratios.
Yeah, the gas to dust mass ratio is also low. The gas to dust mass ratio is around 10 to 1. 10 to 1, the gas to dust. So not a lot of gas, but those gas are due to from CO observation. And people argue the CO has a big problems. Yeah, frozen out at the mid-plane. Yeah, yes, right.
So my question is that how skewed this benchmark is compared to average disk? Because when you
Right,
use those
right.
finite occurrences to compare.
Yeah, so this will be only for the massive stars, massive disks.
Top 1/3?
Yeah, it's almost like these. It's almost like the top, maybe the top like 20%.
20%.
Yeah, the massive ones. And if you buy the optical thick argument, basically the bigger they are brighter. So basically we are not saying the disk is more massive, it's just that they are bigger. So all of these disks are big, right? All of these are big, and all of these are small. Right. Because you can only see big dust, big disks.
What are
Right.
the sizes? The C#? Is there like
Yeah, so these are all, for example, this one is like 100 AU, AS209. This is 200 AU. This is 200 AU. It's a 5.
like 10 AU?
Oh, no. Most of them were around 50. For example, if the. Oh, this one. Most of these were compact disks, less than 30 AU. Yeah. They are unresolved. That's why they are less than 30 AU. They are unresolved. Yeah.
So these disks are big enough that you expect there to be some significant photoionization or X-ray driven mass loss.
Right, at the outer part.
Does mass loss affect any of these processes in terms of how the structure responds to a given set of plans? It's a longer term thing, of course.
Long term, yeah. It may change the shape, the outer gap edge. Could expect.
Change the dust to gas ratio
You.
if particles are trapped in places.
Right. You are concentrate more dust. Right. That is one argument people say why the gas to dust mass ratio is 10 to 1, not 100 to 1, because a lot of gas were photo evaporated away.
Sure.
So you concentrate more.
There's a global effect in the composition.
Right.
But I mean,
Yeah.
the question is more just the detail.
Yeah. So I'm not. Yeah. I'm not.
It's nice to get a
Yeah.
coherent alpha value. Same alpha value for every disk at the
Well,
same
they should
shape.
take this guy.
But if you use every different alpha with every different disk, it becomes
reason why
like
they should
24
not
hours.
But there's likely to be big feedback protection. I mean, the particles are going to feedback.
I think in the outer disk, as you said, probably the cosmere ionization is dominant, so it shouldn't really matter too much. Depends on the disk.
No. Yeah, it's hard. We also did MHD simulation on accretion process. It depends on the field strength too.
Densities of the gas are we talking about here?
Right. So in some of these, the tumor, actually these disks are pretty massive. The tumor Q, you average them is around 5, around 5.
It's low enough bias for cosmere.
But I'm arguing that even here we are underestimating the mass. The mass could be make Q equals 1. So, but these are already the most massive disks normally in protopan disks, and the tumor Q is. Yeah, I mean the average at the outer part here, people argue the Q is around 1 or 2 at these summer rings.
But Q equals few disks, say, and
100 years, it's not that high.
Yeah, it's not that high. So that's these ones people say they can be objective. At 100 you still reach to I think more than 10 grams per meter square. X-ray reach to could go 100. Right. Okay. Yeah.
Speaker again and
Yeah. Thank you.